In this presentation, I'm going to show how to use fast RTA tools within Fekete Harmony to analyze unconventional reservoirs. Here we have a gas well from an unconventional play, and we've got a few months worth of production data and flowing pressures. And we want to apply some of the principles that were talked about in the first video and determine some reservoir characteristics, and most importantly, production forecast and expected ultimate recoverable reserves. So let's go to the analysis. We're going to start by looking at a log-log plot, and the Fekete type curves provide a convenient backdrop to a plot like this, because you can, in addition to seeing the shape of the data itself, you can very quickly ascertain as to whether you're in the transient part or boundary dominated part of the flow regimes. In this particular case, the shape of the data I think fairly clearly indicates that we're not in the boundary dominated flow regime. And the reason I'm saying that is if we look more closely at the tail end of the well performance, it significantly overshoots the upper limiting decline curve, which is a harmonic type curve shown here in dark blue. And so the data being well above that curve indicates that there's still significant transient flow inside this well. We're not necessarily seeing a half slope, which would be indicative of linear flow, but as you'll recall from the first video, the presence of damaged skin may well be masking the half slope that would normally appear as a result of linear flow. So we need to look at more, maybe some different types of plots to try and figure out what's going on here. And really that's what RTA is all about. It's about looking at several different diagnostic plots and trying to come up with a qualitative interpretation of what's going on. So we haven't drawn a conclusion yet as to what we have here. The only thing we know for sure is that we have some transients in the data. This production has not yet reached boundary dominated flow. Let's take a look at the Wattenberger plot. This is also a log-log plot. The difference being here that the type curves are designed specifically for a linear flow system. So the backdrop that we see here is predefined for linear flow, and we also conveniently have a derivative plot here. The derivative plot can help us see the half slope in linear flow, which may otherwise be masked in the production data. The blue data shown here is the derivative plot, and as we can see, it does exhibit a fairly clear half slope, at least within the middle part, or the bulk of the data in the middle here, and that would be the half slope right there. The raw production data shown in red doesn't show this same half slope, most likely because of the presence of damaged skin. So again, this is just a qualitative diagnostic plot. We're not really going to be too concerned with the numbers, just trying to get a visual sense for what's going on in the data. The next plot I'd like to take a look at is our unconventional gas module. And the unconventional gas module ties some of these different diagnostic plots together and will allow us to come up with a complete assessment as to what's going on in this system. And if we start in the top left-hand corner, we have our square root of time plot. And as we can see here, the square root of time plot clearly shows a straight line, which would confirm our linear flow suspicion. In fact, I like to see a half slope on the derivative plot on our Wattenberger analysis, and a confirming straight line analysis on our square root of time plot. Then I'm pretty comfortable in saying, if I see both of those things, that I have linear flow. So I think what we're looking at here is pure transient linear flow. We do not see any departure from the straight line, which would suggest that we have not reached the end of transient flow yet. We're still in infinite acting linear flow. So the position of this green line, which is determined from the extrapolation of our flowing material balance plot on the right-hand side, at the moment is too pessimistic, because it's indicating that boundary dominated flow is occurring earlier in time In fact, we're still in transient flow all the way to the end of the data. So I'm going to show you how these two plots are linked together. If we scale the axis down here a little bit, and now I change the extrapolation of the flowing material balance plot, you can see that I can dictate where that green line is going to be set. And to get the proper P90 assessment of the stimulated reservoir volume, I want to put that end of transient flow right at the end of the data on the square root of time plot. That's indicating a minimum stimulated reservoir volume. And our flowing material balance extrapolates to an original gas in place, in this case of about 2.7 BCF. On the bottom left-hand plot, we have a log-log interpretation. We've got our log-log flow rate versus time data plotted here. In addition, it plots a type curve overlaying that data, which represents our model. The model being, as we talked about in the theoretical discussion in the first presentation, a modified hyperbolic decline curve consisting of transient b value equals 2 and then boundary dominated flow once we reach the boundaries at the end of the data. So that's what that type curve is representing. That's the red type curve. The brown type curve assumes that linear flow goes on forever and is not bounded by any drainage volume. The red curve is bounded by drainage volume that's consistent with the end of the data, or transient flow ending at the end of the data. So the red type curve would be a pretty good P90 forecast and EUR for this well. Just to show the interplay between these plots, we can move this data up and down. What we're looking at right now is changing the skin. When we change the skin, we change the shape of the curve on the type curve on the log-log plot because it's a production rate plot. It changes shape. However, it doesn't change shape on the square root of time plot. The slope remains the same. It's only the position of the straight line that changes. If this line goes through the origin, I can be very careful to put it right through the origin right here, this then becomes a perfect half slope. So it is falling 1 log cycle for every 2 log cycles it goes across. So that would be our pure linear flow. And the difference between that solution and the actual solution is the damaged skin, or the apparent skin that's been imposed on this system. As you can see, it's significant. It has a major effect on the production data. So if we move this back into place again, we can then nicely match the data to where it should be. We can also change the A root K. The A root K is adjusted by changing the slope of this line. Normally the slope of that line is something that can very easily be locked into place. We probably don't want to mess with it too much because we have a lot of data which shows very clearly where that straight line should be. So that's one of those parameters that I think is very well known from this analysis, as is the intercept on here. The main unknown, or the main uncertainty in this interpretation, lies specifically in the assessment of this drainage area. We just don't know what the drainage area is. What we've got in here right now is a good minimum, but we don't have a sense for what it could be. If we look at the forecast plot, and I'm going to expand this to get a more clear view of what's going on. If we look at the forecast plot, this is simply the same information that's shown in the type curve, except in linear format, which makes it a little more convenient to look at as a forecast. So this is our production forecast for that P90 case that I talked about. We can limit it either with an abandonment rate as shown here, or we can limit it by changing the end time. If we wanted to make a 30-year forecast, we could have it extend further in time and have it go on for whatever time period we like. So I'm going to minimize that again back down to here. And so really all these plots are connected together. Now, there's a couple more things I can do with this. If I want to put on or include on here additional forecasts representing different drainage areas, you'll notice that our stimulated reservoir area right now is 33 acres. That's consistent with our minimum extrapolation to minimum original gas in place. So in reality, the drainage area could be and probably is larger than 33 acres. So what I would propose is that we try a forecast for a drainage area of 40 acres and then maybe another one for 80 acres. And in both of these forecasts, I can specify the decline exponent. This has been defaulted to a value of 0.5 with lacking any other information about how heterogeneous or homogeneous this stimulated rock volume is. 0.5 is a good conservative number to use. If in fact we have some fractures that are very closely spaced together and others that are more sparsely spaced, this b-value could go up significantly. It could go as high as 1. Potentially it could go even higher. We're not necessarily limited by that. But we're going to keep that as 0.5 for now. So as soon as I hit OK here, we get a series of additional forecasts, and I'll expand that so we can see them more clearly. We can see we still have our P90 forecast, which is for our minimum case, and then we have another case, which is a forecast that is consistent with a drainage area of 40 acres, and that gives us an EUR of 1.8 BCF, and then another forecast that's consistent with a drainage area of 80 acres, which gives us an EUR of 3 BCF. Now the fact of the matter here is we have absolutely no idea which one of these forecasts is the right one, or maybe whether it's one in between, because we have not seen the boundaries yet. So we have to keep watching this well and updating its performance to get a better idea of where this, directionally where this data is going to go. Since we're still in transient, we really don't know when it's going to start curving over and what the ultimate recoverable reserves is going to be. There is another step that we can go with this. We basically have our forecast here at this point in time, but we can enter in, if we enter in a known effective well length and number of fractures, we can actually calculate the matrix permeability under this assumption. So we're going to do that. We're going to put in our well length and the number of fracture stages. And assuming that there is one single fracture per stage, and they're evenly spaced and all of the same length, then our matrix permeability would be 0.00057, which equates to 570 or 571 nanodarcies. If that is a number that we think is consistent with what we believe the matrix permeability to be, then it stands to reason that we probably do have a single fracture per stage, and they're all fairly uniformly distributed. So this can give us a little bit more information. Let's look at a different scenario though. Let's say on the other hand that we had independent information, for example a core analysis, in which we knew or suspected that the matrix permeability was lower than this. Let's say that we believe that the matrix permeability is only 100 nanodarcies. Well, in that case, I can type in 100 nanodarcies in here. And what I'm going to see is that my drainage area has become larger. My drainage area is now 79 acres. So now we are allowing the matrix permeability to specify the size of the stimulated rock volume. And we need to be careful doing this because it really depends on the quality of the information that we're providing here. But if we do have an independent estimate that suggests that matrix permeability is a certain value, we can use that matrix permeability to determine what the area is. Keeping in mind now that this is no longer an area that comes out of well performance analysis. It's being specified using an independent estimate of matrix permeability. So this one could actually be a good say P50 interpretation or forecast, because it's using sort of all the best known information, but is not necessarily a minimum or P90 value. Once we've completed this whole procedure and have a forecast that we're happy with, let's say that we're happy with this one as our P50 forecast. There are some additional type curves on here as well, but the analysis method is going to remember the 79 acre analysis. So there's really only one stored interpretation here. The other type curves are just for comparison. What we can then do is put this on a rate versus cumulative plot as a new worksheet. And so I'm going to add in a decline curve here. rate versus cum, and I'm going to put my unconventional analysis on there. And now that can be basically my reserve interpretation for this well. What I could also do, if I was so inclined, would be to add a simple decline curve, exponential decline curve, and compare it to the curve that I've obtained using my unconventional gas module interpretation. Or maybe, if I want to do a best fit and do a comparison of that best fit, I can now compare those two forecasts together.